This video series starts our first class on a series of classes where we look at applications of derivatives. So in this video, we're going to look at one major theorem called the mean value theorem. Future videos are going to extend that into the extended mean value theorem, and then also look at another application of derivatives called L'Hopital's rule that utilizes limits. And in that spirit, let's look at this warm-up question. So calculate this limit. This should require some previous skills, so you should be able to pause the video, try this out, and resume the video when you're ready to see the solution. Okay, the solution. As you might recall, with limits that go to infinity, we have to multiply the numerator and denominator, if it's a polynomial expression, by 1 over the highest appearing polynomial, so t squared. 1 over t squared to both numerator and denominator. When we do that, we get limit as t approaches infinity of 1 over t plus 1 over t squared, and then all over 1. Okay, and then with this, we know what these limits are independently, and so then we can just calculate them. We get 0 plus 0 over 1, which is 0. I will start at 1. But there we go. So that's our quick warm-up question. We will see limits return in a moment. And so we're going to just kind of do a hard shift and look at a major theorem that uses both the average rate of change and instantaneous rate of change. And we're just going to give you the theorem. So the mean value theorem. So it says if f is differentiable on the closed interval. Okay, so we need to make sure we satisfy that condition because that is a hypothesis. So differentiable on a closed interval. Then what this is saying is that there exists a number c in the open interval. Okay, so just to be clear, this is a number in the open interval ab such that, and then f prime at c, so that is the instantaneous rate of change. So the instantaneous rate of change at c is equivalent to or is equal to f of b minus f of a all over b minus a, and we recognize that as slope, better known as the average rate of change over the entire interval. So and then we can rearrange it with algebra as what that equivalently b says. But the idea is that this is saying that the instantaneous rate of change at a point is the same as the average rate of change over the entire interval. And if we want to sketch this, so if we imagine these curves here, right, I'll do the instantaneous rate of change, I'll do the average rate of change first. So average rate of change would look something like, and I'm going to draw a good line, something like that. And so if we look at the slope of this line, that would be our average rate of change. So then we just have to find a point C. Let's see, I'm going to do it maybe about there. So then C is your x value. Go up and you'd find f of c, right? And so this would be f of c. But the derivative at c would have that same sort of slope. So this would be m, which is your instantaneous rate of change. But those two m's are the same. Okay. Similar thing happens over here, where we could look at the average rate of change over the entire interval. So something like that, and I'm freehanding it. I suppose I could use a tool, but oh well. And then we compare that to the instantaneous rate of change, maybe right about here. So that would be our C, and then we could look at the instantaneous rate of change right there. Oh, that's maybe a bit much. Something like that. Okay, so again, those two lines would have the same slope, and showing that the average rate of change and instantaneous rate of change are the same. Okay, now, practice. So we have a function, we want to find c such that instantaneous rate of change at c is the same as the average rate of change, or show that none such c exists. Okay, so what do we have to do? Well, we have to do the theorem, right? So we have a polynomial function. Oh, it's different. Polynomials are always differentiable, so no need to check that. You could mention, like, okay, we should probably just do it. So f is a polynomial, and then therefore f prime exists. That's really what differentiable means. The derivative exists. Okay, and so then maybe some steps here. If I FOIL this thing out, I'd get x cubed plus x squared plus, or minus 2x. And then f prime, then I could calculate as 3x squared plus 2x minus 2. Okay. And then I just need to compare the instantaneous rate of change to the average rate of change, right? So let's do that. So I would say IROC at C would be given by f prime of C, which is 3c squared plus 2c minus 2. Okay, and then I need to calculate the average rate of change. Okay, average rate of change. And so these are our A's and B's, right? So I need to do f of 2 minus f of negative 2 all over 4. 2 minus negative 2. And so then if I do this, f of 2, I get 8, and then minus 0 all over 4, which gives me 2. Okay. So then this is where the MVT comes in. By MVT, okay, I would set those two things equal. So 3c squared plus 2c minus 2 is equal to 2. So then I get 3c squared plus 2c minus 4 is equal to 0. And then to solve this, we need the quadratic formula. So c is equal to negative 2 plus or minus square root of, let's see, be it 4 plus 48. So that is 52 all over 6. And then simplifying, I can take out a 2 out of everything. So I have minus 1 plus or minus square root of 13 over 6. And so then I have c is equal to negative 1 plus square root of 13 over 6. And then also negative 1 minus square root of 13 all over 6. And I know that this first one is definitely going to be in the interval. That's okay. This one I would need to check, right? I'm a little nervous that this value would not be, oops, that should be, my bad, I made a error. That should be a 3 in the denominator on these. I would need to check that both these values are within my intervals, you know, negative 2 to 2. And so the first one I know is going to be in there. Second one, it looks a little suspicious, right? So negative 1 and then square root of 13 is like 3 and change. If I divide that, it'll actually be in there. It's just a little suspicious to begin with, okay? But always check to make sure that they're in your interval. Otherwise, you have to toss them out. Okay, next example. Okay, at 8 a.m. the car's speedometer reads that. At 8:10 it reads 50. Okay, show that sometime between 8 and 8:10 the car's acceleration is exactly that. Okay, so let's just think about a little structure here. So I'm going to begin t is equal to 0. That's at 8 a.m. Okay, and then since we're in units of hours, 8 to 10, so I'm going to say 2, t is equal to, and then that's 10 minutes, which is 1/6 of an hour. So I'm just going to say that this is going to be our interval. So that means we're working on the interval 0 and then 1/6. Okay? And here I'm going to say f of x, f of t rather, I should change this, f of t is the speed, let's see, at t hours after 8 a.m. Okay, because then, okay, now we have two different speed measurements, right? So 30 to 50. Okay, so then if I look at the average rate of change, this would be 50 minus 30 over 1/6 minus 0. Okay, so this is 20 over 1/6, which is 120. Okay, there's our 120. Okay, so I calculated the average rate of change. Okay, so I just need to make sure, okay, so then maybe a question is, f prime of t, does that exist? Well, yeah, so as we think about why a derivative might not exist, are there any breaks? Are there any gaps? Any sharp turns? No. And I'm going to say exists because acceleration is smooth. Oops. So when I say smooth, it just means there's no breaks, gaps, quick adjustments, right? You have to go slowly, well, or not, but you have to transition in a smooth way, okay? And so then I'm going to say that this is equal to f prime at c, and then I'm just going to say by mvt, okay? And so I think I've done this because this, my friends, if f was speed, this is acceleration. Okay? So I think I have the outline. I might just say, you know, by mvt this is equal to f prime of c, so then I should say that, you know, there is a time in 0.16 such that speed, or that acceleration, the car's acceleration is 120 miles per hour squared. Okay, and that's going to satisfy the problem. So again, mean value theorem, all about comparing average rate of change to instantaneous rate of change.